There we go. All right. So basically, guys, a time series is a series of points. Now, usually we do formulate any time series like this. We want to explain a given variable with other types of variables that each depend on, for example, in econometrics 1, you guys saw that you could explain one variable with a set of others. With time series, you can do the same. However, those other variables, or in this case, the lags of itself, also have timestamps. Now, these timestamps are either lagged values or forward values, or if it's another variable, it can be coinciding values of in time. Now, most commonly, time series are basically a sequence at equally spaced points in time. Say, for example, we want to model something that it's in days, something that it's in weeks, something that it's in months, years, etc., seconds maybe. So, for example, maybe you want to forecast the weather. Time series are used for that. Sales for a given company, say it's groceries, website traffic, stock market trend, stock market predictions, and many more. So time series analysis is useful for us in order to extract meaningful information about this kind of series. And also, analysis allows us to do forecasting. Now, forecasting might sound like predicting the future, but what it actually is that we can try to predict with statistics how any given series will continue to move in the future by using how it's behaved in the past. Now, there are many models that we can use for this kind of stuff. The main two that we are going to focus on are autoregression and moving average. Now, an autoregressive process is, for example, in the screen right now. So an autoregressive process is a time series that can that has a variable to explain, in this case yt, and what it uses in order to explain that variable is the previous values of that same variable. In this case, yt minus 1, yt minus 2, etc., all the way towards p in this case. Now, p in this case would be called the order of the AR. So imagine we can have a given time series that's an AR model that, for example, imagine it's the weather. So if it's the weather, then you're trying to forecast the weather today. How are you trying to forecast the weather today? You're giving it a variable c, which might be the expected structural value in temperature of the weather. You're giving it the yesterday's value in temperature times the sensitivity that yesterday's temperature has on today, the same way for the previous day, and so on, plus, and this is usual in any kind of econometrics, you're giving it an error term. So any kind of explanation and any kind of prediction can never be perfect. So you always have to include this noise term. So this term captures whatever jitter you might have in your data. And it's very useful because if you do not have any kind of error term, then imagine you have a bullseye board. So in a bullseye board, there are several circles for different multipliers of points. So if you wanted to give it an estimation of maybe, do you want to actually always get on the center? So if you try to model uh, a shooting approach in to always give it in the center, that's much harder than trying to model an approach that you always get within the first two inner circles. So this error term allows us to flexibilize our precision in the modeling. So far, any questions, guys? Okay, I guess not. So before going on with AR, there's a question. That last one, so the bullseye. Okay, so go back to econometrics one and think about how you want estimators to be. And you might you might recall the term blue, your best linear unique estimator. So imagine you have a bullseye, and which is easier to do? Perfect the method to always hit the center, so straight out the center, or is it easier to train yourself in order to always hit the first two inner circles? So in one, so in the approach, you always need to hit one point. In the second approach, you always hit an area of points. Given it's a reduced area, but it's much larger than just hitting one specific point. The error term allows us to flexibilize this trying to model something. Is that clear, Sophia? Okay, awesome. So before moving on, we have to introduce or maybe recall one term, which is stationarity. Now, stationarity is a very important term in time series modeling. And so why do we care stationarity? For starters, what does stationarity mean? Any guesses? No variation. Could you explain further, Carlos?
Yo estaba pensando como que todo se centra en un solo punto. Podría ser, por ejemplo, algunas medidas como la media o la varianza, quizá.
Mm-hmm. Yeah, so Carlos is thinking of weak stationarity, and that's usually the way that we think about stationarity. So stationarity means that you are mean. So usually weak stationarity is that you are mean and very stationarity. Mean stationarity means that you have no. So if you look all throughout the time series, the mean doesn't shift. The mean is the same. So for example, in this example, so you have this. Oh, I got a spike. Disregard the spike. Let me try it again. Okay, clearly my mouse is not cooperating, but in this case, if you disregard the spikes, you have stationarity in mean, correct? But if you include those spikes, then what happens? Correct. You have some outsiders, some outliers. Okay. Then you no longer have stationarity in mean, and also without including those spikes, the variance was also kind of stable. By including those spikes, you no longer have stationarity in variance. So it's basically those two that allows you to have weak stationarity. Now, the formal definition is a little bit broader, but in general idea, you have to think about weak stationarity like that. Mean and variance behave the same all throughout the time series. There's also a component of autocorrelation that we are going to see later, but those are the two main main stages. Yeah, that is weak. That is weak. So strong means in any of the moments. So moment one, two, three, all throughout infinite. So in strong you would have um, skewedness, the same way all throughout the time series, kurtosis all throughout the time series, torque all throughout the time series, and all the other fifth, sixth, and to be honest, I don't know the terms for six to towards in moments. So that is a stationary, and why is this important? Check which model to use. So that is kind of correct. So without stationarity, we cannot use the two models that we are going to focus on. Now, the first one being autoregressive processes, and then moving average processes. Now, again, to repeat, so in order to be classified as a stationary time series, you need the mean of the series doesn't have to be a function of time, so it has to be rather constant. Call. Let me reject this call. There we go. The variance of the series also should not be a function of time. It should be homoscedastic, which means that all throughout the time series you have the same variance. Homo as the same, sedastic as variance. And also the third term that I was mentioning is that the autocorrelation, or in this case autocovariance term, is that the covariance of the ith term and the covariant with the I plus something term should not be a function of time. So basically the covariance, the autocovariance function should be stable and also stationary. Now, if these three criterions are not um, complied with, so if you cannot check all those three boxes, then you need to do some things. Now, one way of taking away some, for example, in this case, if you have this kind of, I don't know what's up with my mouse, so ignore that. I'm gonna use another color of ink. If you have a time series that looks like this, then if you only look at the upward values, then it looks stationarity. However, if you look all the time series of in of itself, then it's not mean stationary because it has a trend. Now there's a process called detrending that allows you to take away this trend. That is one way to correct and make stationary. Now another way is, for example, differencing. Yes, that is correct, Alvaro. Another way is differencing. So, for example, and we're going to see this more in the rest of the course, but there is something called a unit root. And in order to solve that issue, and a lot of actual return series do have almost a unit root. In order to solve this issue, you need to apply differencing. So lagging your series towards yourself, and basically not, for example, not, you cannot model prices, but you can model returns, because returns are the growth of prices, and growth is a kind of differencing, is a proportionality differencing. And yeah, and the last one is seasonality. So for example, some real world data behaves differently depending on which part of the year or of the season it's on. So let's do the obvious example. So sales in Christmas always are higher. So in order to model same-store sales for a given company, you have to take into account this phenomenon, and that is called taking into account seasonality. And we are going to see seasonality further on the course in, I think, in about 2 or 3 classes. But those three are the pitfalls and how to solve them. Also, there are more complex models than AR or MA, so you can also apply those. Now, before before going into the quiz, the moving average process. So a moving average process is the one in which you don't explain the value or the variable with its previous values. You explain it with its previous errors, so its previous shocks, how those shocks still can define the value of a variable. So for example, we usually assume they are distributed normally. Then we can say that, for example, there's a really simple one here below, in which yt is a constant plus its current shock and the last shock. Now, what can you can imagine what can we use in order to explain this kind of thing? Because it's it's not intuitively to think of shocks. Now, for example, think of YT as oil price, right? So commodities also a lot of time have different external shocks that apply to them. In this case, let's think as the error term as natural disasters, like for example, say a hurricane. So a hurricane, say that epsilon t is the events of a hurricane. Now, let's say, for example, that C is, let me pick another color so you guys don't get eye distortion. So let's say that C is 10. Okay. Now let's imagine that the shocks have a persistency of 0.5. Okay. Then imagine that there is a hurricane today, but there wasn't any hurricane yesterday. All right. So the imagine the shock to the hurricane is 5. So ET is 5. And yesterday there wasn't any hurricane. So what is the value that we predict for YT? $15, correct. Why? Because there was no hurricane yesterday, so this is 0 multiplied by 0.5, this is still 0, and then 10 plus 5, right? Now imagine on another example that there is no hurricane today, so ET is 0, this one's 0, but there was a hurricane yesterday, and the hurricane yesterday shifted the prices by 5. Okay. Now, what is the value that we predict now for the oil price? 12.5. Yes. So now let's say there's another example. Suppose there's no hurricane today, and there's so let's stay with this last example. So there was a hurricane. There was a hurricane not today, but yesterday. Now let's go to the next day. If today there's no hurricane, what is the value that we predict for the oil prices? So in this case, what our model looks like. Yes. So let's just stay with this last example, but let's go forward one day. That means that 2 days ago, there was a hurricane. Yesterday, there was no hurricane, and today, there's no hurricane as well. What is the value that we predict for the oil price? Yes, 10. Why? Because our model only takes into account the first lag value and the present value. So if there was a hurricane 2 days ago, our model is not capturing it. So assuming our model is correct, then the oil price for today should be 10. Right? Now, guys, remember, disclaimer, I'm not telling you that in order to model the oil price, you have to look at hurricane data daily. But this is just an example. C is basically the structural mean of the oil price in this case. Hmm? All right, so let me set up the clock. And then we'll start with the quiz. Now, guys, so for the rules of the quiz, first of all, obviously, no plagiarism. It's online. Second, I need you all to turn on your mics. If you do not turn on your mic, then you cannot do the test, the quiz. Third, it's going to be only 50 minutes, so you have to be quick. Get a word with your time. There, it's only I put it in 4 questions. So yeah, it's only 4 questions. So there are quick exercises, but you have to think on the spot, so can be quite challenging. All right, I'm waiting on all of you guys to turn on your mics, else we cannot start the quiz.
Ay, Dios. Siempre mi corazón acelerado. Ay, qué frío.
Having the two Álvaros,
La miércoles.
pero Elber, Nia, Valeria, Viviana, Sandro, Juan Manuel.
Profe, pero tenemos que el quiz con la bulla de todos los micrófonos.
Sí, a mí tampoco me parece muy...
Using Álvaro Núñez, Valeria, and Viviana. Asked it yet.
Gonzalo, una
Valeria,
pregunta. ¿Vamos a tener que hacer la foto?
No, it's online. It's in Google Forms. So, Elber, Valeria. You know, you three in order to start the quiz. Using just Álvaro. What?
¿Dónde está el quiz? No, no entiendo muy bien qué está pasando.
Mr. Idiot. Turn on your mic.
Aló.
Álvaro. Also, Valeria, you have to keep your mic open.
Ay, Dios.
Hola.
No apagues
Using
tu
just
micro,
Álvaro
nada
Núñez.
más.
Mantener el micrófono encendido, ¿por qué?
The quiz.
Solo así puedes dar el... Dale, déjalo prendido.
There you go. Guys, you cannot turn off your mic. You've been warned. And yeah, it's 15 minutes.
Uy, ¿dónde lo...? Ah, ya, ok. Muy bien.
Solo, ¿qué me ponemos? El de Lupe, ¿no?
Any to extend out your grade
¿Para qué es el micrófono encendido?
Vale,
from the measures.
¿Qué va a garantizar? Bueno, no entiendo.
se aúlla.
You have 1 minute to turn on your mic. There you go. Thank you.
¿Qué?
¿Eso sirve?
Sí, eso sí funciona. Puedes enchufarlo para la derecha también.
Punto.
Yo rellenaba por encima porque se me había perdido.
The questions are randomized, so you have content.
Cuando sacaste aquella mano se había acabado, ¿no?
What is the question? Uh, times. Instead of you meant n, right? It's times. Thanks, guys. Yeah, turn on your mic.
¿Me das un finiquito para cambiar mi respuesta?
Start wrapping up because we have a little bit more than a minute, and exactly at the time that it ends, you can no longer send your answers. So remember, you have 65 seconds to turn in your answers.
Gonzalo, yo ya acabé el quiz, ¿puedes ahora que te hayan llegado mis respuestas?
To click send at the end. I don't know where it's positioned, to be honest. It's yeah, it's at the bottom.
Repetir, no te escuché, ¿qué dice?
That you have to click send, else I won't receive your answers and you won't get graded.
Escuchado. Había una interferencia. Escúchame, a mí me parece que se ha registrado mi respuesta.
It's
Que a
good.
ti ya te llegó.
Yeah, I've received 7 answers so far. 8. Yes, Alvaro, you can. 3, 2, 1. No more I'm going to turn off the answer collection. No more answers are received. Okay. All right, that's good. So on average, 2.22. Not bad, out of 2. All right. So let's take a brief break. Not of the class, but of time series, and let's go back to R in order to see some useful concepts for simulation. Now, simulation will be really useful to you, not just in finance, but in programming overall. So I hope you guys attended or saw the recording of the workshop and last week's tutorial, because they were pretty important. So the most easy way to create random values from any given distribution in R, for example, let's say the normal distribution, is using R norm. So what R norm does is that, am I sharing my screen? Yes, okay. So what R norm does is that you give it how many values you want to create, so you want to gather from the normal distribution, and after you gather those values, now you have to give it um, the characteristics of that normal distribution, so the mean and standard deviation of that normal distribution. Now, in this case, we're going to get 10 numbers of a normal distribution with mean 15, standard deviation 2. And how do we know that it's actually from that distribution? So remember, this is our population mean and our population standard deviation. However, we have a sample of 10 values. Now, our sample should go still around over there. So our mean is almost 15. And if we calculate our standard deviation, it should be around 2. So now, since these are random values, if we generate the same command again, we won't get the same values. We get a different set of numbers. They are not the same as these. How can we check for, how can we be so sure? So we can do, for example, now is this the same as our norm example? And we get that it's false. Now, remember, you guys learned, I don't know if it was the workshop or at the start of the tutorial, that you can check all of the logicals at the same time with all. Now, all true? Nope. Okay. Now, how can we solve this? Now, there is a concept called seeds. So, what is a seed? So imagine you have a book that's full of pages of random numbers, an infinite book. And what the seed is telling R or any programming language to start on that line of the book, to start gathering numbers from that line of the book. So if you tell R to set seed 1, so start at the first line, and you run all of this, you'll get this set of numbers. If we seed 1 again and save it to another variable, we'll get the same set of numbers. Now, why is this useful? Because you want your examples, you want your work to be reproducible. You want your investigations to be reproducible. You want your model to be reproducible. So if anyone opens up your work and tries to run it again, they get the same results. That's why seeds are useful. How can we check? Again, all our normal example is the same as our normal example 2, and we get that it's true. So it's exactly the same. Now, if we check, and if we start at seat 2, and we compare these values with the first one, then false. We no longer have the same values because we started in line 2 instead of starting in line 1, right? Another useful function that we looked at briefly last time is sample. So let's get an example vector with numbers 1 through 20. Remember, you can also write this as this. You can also write this as this, 1 through 20. It's the same. So sample takes a vector, you tell it how many values to pull from that vector, and if you want replacement. So replacement basically tells you, so if you replace, then if you pull out a value, the value is still there. You pull out a copy of the value. If you do not have replacement, once you take out a value, you can no longer pull out the same one again. Right? It's like a bag of balls, and you have 3 balls. Let's say you have a red, black, and a blue ball. If you pull out the blue one, and you try to pull out another one, you won't get the blue again. If you do have replacement, then you just pick out a copy of the blue, and the blues, or the original blue, is still there. So you can still pull out another one. Okay? Let's say we sample without replacement. Then we get 15 out of our 20 values, and none of them are repeated because all of our values are unique. So if we sample without replacement, we won't get the same value twice. If we sample with replacement, then we might get a repeated value. Not necessarily, but we might. Then we got 14 twice. No, okay, we didn't get any repeated, but we could. What happens if we do it again? We get a different set of values because sample, just like generating random numbers, are bound to randomness. So in order to get the same values every single time, we have to set a seed. We open up the book on line 2 and we get 15 values. Then we go back to line 2 and we open up 15 values, we get the same ones. Right? Any questions? Alvaro. Alvaro? The default of replace, I think it's false. Sample. Yeah, it's false.
When you put you put a parameter 15,
Yes.
it's like what this means? What it means?
It's how many numbers you're pulling out from your vector.
Okay.
So the
So I have
size
another
of the sample.
I have a question. When you like how that the seed works? I know that get the same numbers, but how that it can get the same numbers? How it worked in the
So think of it as the example of the book. You have a book of infinite pages and as well infinite lines. However, those lines are ordered and they are always in the same order because the book is already printed. Now imagine a printed book with infinite pages, right? But the book is already printed. So if you tell R to go seat 1, then R goes into the first line of the book. And if you tell them to look at the first line again, it'll see the same values. If you tell it to look at line 2, then it won't get the same numbers that if you told it to look at line 1. So let's say, for example, let's say, so I have over here a report from JP Morgan. If I read the first line, it says, within our bullish outlook on global equities, we have recently taken profits on our long-term standing. That is the first line of the report. If we look at line 4, we won't get the same words. If we look at line 4, it's motivated by significant outperformance of almost 25%, blah, 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 blah. All right? So if we think of it as lines in a book or in a JP Morgan report, then we have an index with different values every single time. But if we look at that index, we'll get the same values every single time. Just like if I look, if I go back to this report, I will find the same words in the first line within our bullish outlook. If I put it away and I take it back, if I go to line 1, I will find within our bullish outlook, and it's never going to change. Carlos.
So it's like, okay.
Sure, you can speak.
I can speak? Okay.
Yeah.
The thing was, so you like when you put seed, it's like it specify like a bunch of numbers, and it get
Yes.
like that. Okay. Yeah, I understand.
Yes. That's why there is nothing. Well, at least to my knowledge, there is nothing in any computer science thing as true randomness. There is only pseudo randomness, which means that it looks random, but it's not actually random. It's pulled from a set of random numbers that look random, but since they are already generated, they are not true random. A whole conversation for another time.
Profe, yo sé que no tiene mucho que ver con el curso, pero esa generación, ¿cómo la hacen? ¿Con una ecuación? O sea, ¿cómo generan esos números que
Yes.
parezcan random?
So I think R takes the Perling noise generation. So Perling noise is in this case one-dimensional Perling noise. Takes a function, not a function, an algorithm, in order to generate this kind of numbers.
Es solo una
If you
fórmula
want,
gigantesca, sí.
yeah, it cannot be compiled into a formula, I think. So it's a
Okay.
mathematical structure.
Process. Okay.
Yeah. In order to learn more about Perling noise, I do recommend, for example, Coding Train. It's a really good channel for
YouTube?
coding and visual design in coding.
In YouTube?
Mm-hmm.
Okay, thanks.
Yep. He's a really great teacher. He's an NYU teacher.
Cool, thank you.
All right. Any questions, guys, about sample or seeds or generation?
One time I
Álvaro.
heard that they use. Oh, sorry.
You heard the what?
I think he
No,
raised his
dale,
hand
Carlos.
first.
Dale, Carlos. Sí, no te preocupes. Dale, dale.
I think that one time I heard they use lava lamps to like generate random numbers. Is that true or not?
Yes, there is a. I think that's in Sweden. That's
real?
Yeah, it's completely real. So what they do, and I'm sorry for the other guys that I'm losing a little bit of time in this, but it's a really cool example. Remember that pseudo randomness for some things might not be enough. In order to, and this company, what it does is encryption. So to encrypt data, what they do is they have a wall full of lava lamps, and the behavior of where the ball inside, so the plasma ball inside a lava lamp moves, is really, really hard to predict. So if you have a wall full of them, it's even harder to predict the behavior. What they do is take a picture of their lava lamp wall and map out the positions of the balls inside the lava lamps, and they use that in order to encrypt the data of their customers. So
That's
the
really
only
interesting.
way that they can decrypt that data back is using that photo.
That's very
and
interesting.
generating that's not one dimension, right? That's two-dimensional encryption because you have a picture.
Uh, teacher,
Yeah, sure.
teacher. So what I understand is like e-views, data, and all that programs like they just already have the groups of random variables and they pick one like that.
Correct. That is
Uh, so,
correct.
so it's not random at all. It's just more like
Are
predetermined.
you disappointed?
Yeah, I was thinking, what? Yeah, what the hell? But okay, yeah,
Don't worry.
yeah.
Álvaro.
Thank you.
All right. Any other questions, guys? Okay. Let's go towards thinking of the law of large numbers. So we introduced this topic the last time, but let's check out an example. So, and I'm sorry for this. Forgot to change this. There you go. So, let's take an example. So if we have a distribution of mean 172 and standard deviation of 542, and we allocate a vector of means. So why am I creating this vector before putting in the values? It's because that if you pre-allocate memory, now in this case it's only 50 values, so it won't really make a difference. So, but if you're working with millions or billions of numbers, then pre-allocating memory makes processing much faster. So right now I'm creating a vector of 50 zeros, but I'm going to fill that vector with with means of distributions generated from a mean of 172 and a sigma of 542, normal distributions. So I'm going to put in the first value the mean of a distribution. I'm going to pull just one value of the mean 172 and sigma 542. So you could have, now the inefficient way of doing it is doing it each time for each number. So in this case, I'm going to do it 50 times because my vector has 50 spaces, 50 slots. So on the first one, what I'm going to do for all of the 50 values is generating the mean of this distribution. Now remember, since I'm not inputting a seed anytime, the value that I will generate in this is different every single time, right? So I just write a simple loop and I get my vector of means. So my vector of means, the mean of my vector of means, in theory, should be, oh, let me do that. My reader. The mean of my vector of means should be around 172, right? That's the law of large numbers. But 50 is not large enough. And let's check out a simpler way in order to do this, because that's four lines of code are too much for this. Instead of 50, let's say 1000 iterations. We're going to use the function replicate. So what replicate does is that for any set of values, for any set of times, it runs a function. So I'm telling R to run the mean of a distribution 1,000 times. And what I get is 1,000 values right at the get-go. So if I do the mean of this, I'm much closer to 172. If I increase, say, every single time I'm closer to 1. This one I wasn't closer, but usually when you increase the number, you should be closer to 172, right? Decrease this so you guys can run it when you get the code. Now, there is another way of doing this. So, for example, let's think of sapply. So what sapply is doing is the same as a for, but in a vectorized way. So I'm giving it a vector of 1 all the way through. Let's change it back to 1,000, 10,000 again. And I'm running the mean of our norm of mu, sigma, etc. Now, mu, sigma, I already have generated over here. And x, since I'm writing function of x, x is the thing that is going to change. So what I'm doing is increasing every single time the numbers that it can get in order to get the mean of the distribution. So in the first one, so in in the first iteration of this sapply, the size of this distribution will be 1, and the mean of one value is just that one value. In the second one, it'll be 2, so it'll get the mean of 2 values. In the third one, it will be 3, and then etc. Up until the last one, where it's going to do the mean of 10,000 numbers pulled from a normal distribution with mean 172 and sigmas 542. If we run this, it's going to take a second. There we go. And if we plot this, now I'm just doing plot in order for rapid sake, but remember, you guys are tasked to learn ggplot. So I don't know if you guys can see the pop-up window. Yeah, you can. Awesome. So the mean is converging towards the true mean. And this is basically the law of large numbers, right, guys? This is like a proof, a practical proof of the law of large numbers. Okay. Now there's ggplot. So this is ugly. Never do this again. How do we do this on ggplot? Let me load up tidyverse in order to have every single thing on my toolkit. So we create a data frame with the number of iterations that we used in every single simulation and our vector means. Then we use that data frame in order to plot. So our x-axis will be the number of iterations, just like in this one, and the y-axis will be our intercepts, our means, our calculated means. We're going to put in a horizontal line in order to mark up our values, and this is just to make it pretty. So simulating the law of large numbers. And we can see clearly again that we are converging to 172, to the true mean of the population. Any questions? Álvaro.
Teacher, can you repeat the line of replace? I didn't understand what was the function of
Please replicate.
replicate. Sorry, replicate.
So replicate, you give it how many times you want to run a certain function. So in this case, iters is 10,000. So we are running the function 10,000 times. Now, which function? Now, the function is this one. It's taking, calculating the mean of a random normal distribution of 50 values, mu 172, and sigma 542. I don't know if you need something else.
So it's like I don't know, 10,000 of means that you get
Exactly.
like that.
Yes.
And for that 10,000 of mean, you get an extra mean for all that means,
Yes.
or
We are calculating the mean of this vector of size 10,000 in order to check if actually, we have proven the law of large numbers by getting something really close to 172.
Yeah, but the extra mean of all that means is where?
Hopefully 172, right? Really close to 172.
The mean that you put in the right is the mean of all means.
Yeah, correct.
Yeah, I understand. Yeah, okay, thank you.
Gonzalo,
Yeah.
excuse me. I have a question about R actually. What's the difference between the pipe sign and the plus sign? How do they work?
So the plus sign, it's used in ggplot terms as in to add a layer to the previous one. So what this one does is just takes our data frame and turns it into a ggplot object, but you haven't actually plotted anything. So if I take this away, and if I just run this, we have a blank canvas, right? So with this blank canvas, we're adding a layer. Now, what this layer is telling you is putting points with two axes. Now, the first axis being my iterations, and the second one being the vector means. So if we run these two lines together, we get a simple plot. Now, to that, we are adding a horizontal line with the intercept at mu, which is 172. So it's like building a cake with layers. To that, we're applying a theme. And to that, I'm applying a title. And you can continue so forth and so on. Another thing that you asked was the pipe, right? So the pipe is called a magritter connector, also a pipe. You can put it with Control Shift M. We talked about this fully on the workshop on Saturday. What it does is give the thing on the left as the first argument of the function on the right. So what this is doing is we're calculating this data, now calculate the mean of the data. So it makes code more readable. Is it fine, Omar?
Okay, yeah, thank you.
Awesome. Thank. Alvaro.
Teacher, but if you don't put the mean on the right that you have talked recently, it shows you all the means, or it don't show you
Yes.
anything?
So if we erase this, we get the vector of 10,000 numbers.
Okay, but it's a vector, right? It's not like
The vector, yes.
It's like with columns. Okay.
Vector,
So
yes.
it's just like putting all the formula in those brackets of the mean. Is it just that's the function of the pipe?
Correct. It's like if we call this, a, and then we put mean of a. It's exactly that. That is actually what it's doing, to be honest.
Okay, gorgeous. Thank you.
Right. Let's keep this plus on. So basically, you can do simulations in several different ways. For example, a really common programming exercise is trying to simulate pi by generating the numbers inside a plot. So let's set up our seat. Remember, whenever you're doing simulation, always try to set up a seat. 42 because Hitchhiker Guide to the Galaxy. How many numbers we're going to generate? It's 5,000. 50,000? Yeah, 50,000. Then we have to generate our space. So in this case, the circle is always looked as the unit circle. So from -1 to 1 in a Cartesian space, right? So we're going to generate 50,000 numbers in this space. And what is the formula of the circle? So what is the function of the circle? Is x squared plus y squared, right? Now, if it's less or equal to 1, this function, it means that it's inside our unit circle. So this is just a vector of logicals that we have generated of 500,000 elements. Okay. Now, the value of pi is actually this formula. Now, the rationing behind that formula, I want you guys to Google it up because it's easier to explain, but it's very mathematical. It's just the formula of pi, to be honest. And we're going to plot it. Now, if we increase the number of simulations that we're going to do, we're going to get a better approximate of pi. So let's plot this out in simple R. You can maybe do it in ggplot later. So we're making a blank canvas, inserting the points that are on the circle as red and the ones outside the circle as black. And then we're we're going to just put up the title of our estimate of pi. And it's going to load because it's 500,000 points that they have to generate. Just give it a second. Any. Hopefully, there we go. So as you can see, the numbers inside the circle sometimes R has issues rendering so many numbers, but there we go. The numbers inside the circle are red and the values outside the circle are black, thus getting an approximation of a circle, and also we can estimate the value of pi this way. Okay. Now, maybe as a practice, you guys, what you guys can do is, instead of doing it this way, you can maybe use sapply and changing the number n and seeing how you approximate the number of pi, just how we did with the law of large numbers, by increasing our sample size, how closer we get to the actual value. Okay. You can do it with sapply, or you can do it with a Monte Carlo simulation, just like we did with the replicate function. Okay. I will, of course, post this code so you guys can see the instructions. But it's just to practice. You can consult me about it if you want, but it's just in order for practice. Okay, so we have two paths here, guys. Do you guys want to see exercise in R about time series, or do you want to see exercise like econometric exercises by hand, but not in hand, virtually, of time series? We're going to see both eventually, but which one do you want to see first? Both are time series exercise, but on R or outside R? On R? Okay, sure. So the test will have both. Okay, let's do briefly the ones that are by hand, and then and then we'll go inside R. There we go. So let's go back to our PowerPoint. So now that you guys are obviously experts in AR processes and MA processes, so these are examples of exercises, right? So the difference between week And strong stationary lies in the moments involved in the independence analysis of a random variable distribution as a function of time. Is that true or false? That's true, yes. So basically, remember, the weak law is the first and second moment. The strong law includes all moments. Okay, so all moments in the strong law have to be time invariant. With the weak stationarity, the only thing that you need is the first two moments, so the mean and variance. Second question, Alvaro.
Teacher, when you refer to all moments, you're referring that apart from the mean and the variance, you take the squeezeness and the kurtosis, or anything else there is, or
The fifth, so the torque, the sixth moment, the seventh, the eighth, the ninth, and all the way towards infinite.
all have to be constant?
All have to be time invariant.
Okay. No. Well, okay. I listen another definition, but okay. Thank you.
So second question, every MA1 process can be represented as an AR infinite process. Is that true? False? So now this is a concept that I'm not sure if you guys have seen already. Now there is a concept of invertibility, and that for example, if you have a series such as, for example, let's do an MA process. An MA process is just YT ET minus 1. So if we tried to turn this into an AR infinite process, what should be our procedure? So for starters, we have to find the relationship in between the lags of y, because that's how AR works. So in this case, YT minus 1 is ET minus 1 plus alpha. I really don't know what's happening now with my mouse. T minus 1 ET minus 2, right? However, ET minus 1, so epsilon T minus 1, it's on both equations. That means we can replace this one and change it. So let's reorder it and say ET minus 1 is equal to YT minus 1 minus theta 1 epsilon T minus 2. Right? So if we replace this into our original equation, what we get is YT equals ET stays the same, right? And we replace the epsilon T minus 1. So plus theta stays outside yt minus 1 minus theta 1 epsilon t minus 2. Now we start getting, so if we do it again for epsilon t minus 2 and then epsilon t minus 3, what you start to get is a theta 1 that's growing and growing and growing, right? So a theta 1, so let's just solve this one. Epsilon t plus theta 1 yt minus 1. So we started getting the AR component minus theta 1 squared epsilon t minus 2. So if we started replacing again, then we would get theta 1 cubed, then theta 1 to the 4th power, to the 5th power, to the 6th power. Now what happens if in this case, so this is a real simple example, but in this case, if theta 1 is greater than 1, what happens with our time series? Hello? What happens when you have a greater than 1 number to the power of a really big number? No, a greater than 1 number. Imagine that theta 1 is equal to 1.5. Yes, it tends to infinity, but you cannot tend to infinity. What we call it is that it explodes. Okay, so because a time series explodes, then it's no longer stationary, right? So in order for our time series to actually be represented with an MA or an AR process, then we need it to be, in this case, this needs to be in absolute value less than 1. And that's what we call invertible. Now, this case is easy because it's just one root. But whenever you start adding terms, so an MA2, for example, or an MA, etc., or in the case of an AR, that it can also be turned into an MA infinite, the roots have to be in absolute value smaller than 1. So the roots of the equation to solve out for, in this case, the thetas. Since we only have 1 theta, then it needs to be smaller than 1 in absolute value. Okay. Any questions about that? Just remember your maths free class for this. Álvaro.
Sure, I have a question. When you refer to root, you're referring the coefficient that is with the white noise of 1 lakh, right?
So if you recall maths free, you used to model your differential equations depending on which professor you took it from. In this case, let's use the lagged indicator. So ET, let's put the YT on the other side. So in this case, it'll be minus theta 1 YT minus 1 plus this one. So an ET will be 1 minus t minus 2, which means a lagged indicator towards the squared, theta 1 squared. So the root in this case would be the solution of this equation equal to 0. Yep. I do want you guys to do some overview of your maths 3 and 4 starters of time series calculations. It will be very useful to you guys for this course.
Teacher, but if we have, for example, a model of two lag, you have to have two roots, right?
Correct.
Like that. Okay, okay, okay.
Yes.
Yeah.
So you would have theta 1 and theta 2. But the general procedure is the same. And that's what it's called invertibility. So MA towards AR is called invertibility. If we go towards the next one, a finite MA process is always stationary. What do you guys think? Now, finite means that its component is less than infinite, right? So it's, let's say, MAQ, or yeah, and Q being less than or infinite. So remember, in this, when we talk stationary, we almost always means weak stationarity. It's false. Aha. Why is it false? Good. Good, good. So not false. Well, so it is okay. If you actually take the always, like really straightforward, then yes, it falls. But one, remember, a finite one. So in the other case, the AR infinite wasn't stationary, but the MA process was stationary. Okay, that's one. The so in this case, if the so you're right, Alvaro, in that if you put always, then it is false, and I'm going to grade the solution to this in order to reflect this. But if you have an error term that it's a white noise, then it is always stationary. How? Because if we get the variance of this process, then we won't get any time variant term. If you look at this, we only have the coefficients and the variance of the error term. Also, since it's a white noise, then all the shocks are not correlated in between each other. That means that our expected value, also the expected value of a white noise term, is 0. So we get an expected value of 0 and a variance that's not infinite and, very important, not time variant. So it's time invariant. Okay. Any question with this, guys? Allora.
Why the variance is 1 plus the sum of the betas square? No.
So
Power.
because there's no correlation variance in between each of the terms, you only get the variances of each one of the terms because it's a white noise. So in this case, what you have is that in order to apply variance, so this is really a really useful way of thinking variance. So variance is a covariance of something with itself, right? So you can write variance as covariance of yt with yt. Now, if you replace the values of yt with the process generating function, then you have the covariance of epsilon t minus beta t et minus 1 minus etc 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 with the same thing, et minus beta t epsilon t minus 1 minus etc etc etc. So if you do the covariance, so this is a property of covariance that I think you guys should have seen on econometrics 1, but if you don't know it, it's really useful. So covariance with sums or residuals allows you to do each term within each other. So covariance of ET with ET is what? The variance of ET, right? And the variance of ET is sigma squared. So we have sigma squared. Now, covariance of ET with minus beta t ET minus 1 is 0 because a white noise doesn't have any covariance with its previous lags or its future values. So that's 0. Then ET with the next one, again 0. ET with the other one, 0. 0 and null throughout the series. So we go towards the next term, minus beta t ET minus 1 with ET. Now we've already said that's 0 because there's no relationship in between the different values of time of a white noise. ET minus 1 with ET minus 1, there we have a relationship between, because it's the variance of ET minus 1. So we multiply both BT, beta t, and we have plus, exactly, no other covariance between errors that are white noise. T squared and sigma squared. Now for the next one, we have the following. So it's plus beta t plus 1 or minus 1, whichever. It's minus, it's plus, okay. To the third power. No, it's squared. Squared sigma squared, etc. So we solve this out with this simplification. Nothing more than that. Is that clear, Alvaro?
Yeah, I remember. I remember. Thank you.
Awesome. No problem. But that property of the covariance is really useful in order to separate the terms and do it with each other. It will help you guys a lot when you guys are calculating autocovariances and autocorrelations. Let me go back to this one. Okay. So exercises. Do we have time for 2? Maybe we have time for 2. So an insurance company uses the following model to forecast accidents. YT. So this process is what kind of process, guys? Is it an AR? Is it an MA?
ARMA.
Mm-hmm. It's a combination of the two, because one, you have a lagged value of the variable that you're predicting, so YT. So it has an AR component. And it has a lagged value of the shocks. So it has a moving average process component. Because you're combining the two, that is called an ARMA model. And this ARMA model is of order 1, 1, because you have one lagged value of the AR and you have one lag value of the MA. So it's an ARMA 1, 1. Okay, so where YT is the number of accidents and mu T is normal 0, 1. Okay, so we have a really nice error to work with. Identify the model. Is it stationary? Is it invertible? Calculate its mean and variance. So the model, we've already said that it's an ARMA 1-1, right? Now, is it stationary? How do we define if it's stationary? Now, a really quick and dirty way in order to define if it's stationary is, remember, on this one, we said that if you can turn an MA process into an AR infinite process, it's called invertible, right? If you can turn the AR component into an MA infinite, so the other way around, that is a way of telling if a function is weak stationary. So if we do the same thing again, so the root of the AR component is 0.3. 0.3 is less than 1 in absolute terms, so it's stationary. Again, we can do the same thing with invertibility. So minus 0.7 is less than 1, so it's invertible. Now, again, this is really straightforward because we're looking at order 1s. When you go to order 2 or forward, then you need to look at the whole equation. And we'll see later, hopefully, if the time doesn't beat us, how to do it really easy. Spoiler, it's using that lag operator that we saw just before. The expected value. So the expected value, how do you calculate the expected value easily in this kind of a function? You do this. So you have yt is equal to 0.3. Okay, I'm not going to rewrite this. This was dumb. So if you put it unconditional, remember this is really important. Unconditional expected value is not conditioned to anything. So this is the general expected value of the whole process of yt is equal to 0.3 expected value of yt minus 1. And remember, we said that this process is stationary. So that means that the expected value of yt should be the same expected value of yt minus 1, right? Then ut is white noise. It's not white noise, but it's what? It's a normal 0, 1. So it's a standard normal. What was I? Yeah, so because the process is stationary, we're going to say that the expected value of yt should be the same as the expected value of yt minus 1. So we can rewrite this as the expected value of y. Again, I don't know why my mouse is doing that, but expected value of y. So these two values are the same. Then minus 0.7 expected value of mu t minus 1 and expected value of mu t. Both of them are 0. So plus 0. So if we move this towards the left side, we have that the expected value of y is 0 divided by 1 minus 0.3. Then by knowing this, 0 divided by any number is 0, given that a number is not 0 or infinite, so it's defined. We have expected value of 0. The same way we can get the variance. Again, using the covariance within of itself, it saves you up on the calculation. For time's sakes, I'm not going to do the whole process, but you guys know the following. So let's go forward. Calculate the autocovariance and autocorrelation functions from 0 to 3. So autocovariance, we kind of already saw the autocovariance 0. So autocovariance 0 is the variance because you're doing autocovariance within itself. Autocovariance 1 is the autocovariance with your first lag. Autocovariance 2 is the autocovariance with your second lag, and so forth. So we have to calculate up to 3. So in this case, autocovariance 1, autocovariance 0, we already said it's the variance. Autocovariance 1 is with your first lag. So you can always use the previous autocovariances in order to save you up on the calculation. So if it appears that you have yt with yt minus 1, you can replace it with gamma 1, which is the symbol for autocovariance 1. The same way with all the others. So if we find this one, we can just replace it with the value that we previously found. So we know that mu of the error is 1, so we replace that as well, and we get the first autocovariance. We do the same for the second one, we do the same for the third, and so on. Okay, and we can find a pattern, right? In this case, the pattern is at 0.3 with the previous autocovariance. Now, autocorrelation is very similar. Autocorrelation is just your autocovariance divided by the variance. So for the first one, we do 0 with 0. The first autocorrelation is always 1 because you're correlated with yourself in a perfect status. Autocorrelation 1 is autocovariance 1 divided by autocovariance 0, which is the variance. Autocorrelation 2, autocovariance 2 divided by variance. Autocorrelation 3, autocovariance 3 divided by variance, and so forth. And also, you can see another pattern with the autocorrelation. Okay. Oh, I'm out of breath, guys. Any questions? Allora.
Professor, to get the fact, you have to replace, for example, the fact one, you have to replace the ET of to all the expression that we have, right?
Correct. So over here in the C, so covariance, you replace yt with the whole process, and you replace yt minus 1 with the whole process, but lagged.
Teacher, and you have a book to read this, because I have the Anders, but I don't know if you have an order for finance more specific.
I do, but it's more with I do. So and it's on the it's on the syllabus actually. It's the SAY, TSAY. Ruesay, I think it's his name. That one is applied to finance, and Say has written not only the book on the syllabus, he's reading several books about this topic. So financial modeling in econometric modeling.
Thank you very much, teacher.
No problem. Let me quickly search up the title of the book. Hold on. Materials, books. No, I have a whole folder for Say. Say. So I think it's this one. This is one, and this is the version with R.
Teacher, in both there is this subject, right? Or...
Yes, yes, yes. The second one is a little bit more advanced than the first one, but you can use both.
Yeah, thank you.
No problem. Okay, so rewrite this model as an AR infinite and as an MA infinite. So like we said, since it's stationary, we can turn it into an MA infinite. Since it's invertible, we can turn it into an AR infinite. Okay. Now it's a lot of replacing, but there is a way of doing it faster. Okay, and that way is doing the lag using the lag operator. So let me quickly. So it's let me rewrite the equation. So the equation is yt 0.3, and I'm going to rewrite it with the lag operator. So it's 0.3 L for the lag operator just once yt minus 0.7 L mu t plus mu t. So we can group these two. We can put all the thing with yt on one side and all the things with mu t on the other one. So this is yt 1 minus 0.3. And on the other side, we have mu t 1 minus 0.7. So, and you're going to be hopefully not surprised. How you get the yt? You divide your 1 minus 0.3 and you expand. I forgot the L. And you do a geometric expansion of these. The same thing with the MA infinite one. So you can notice a certain symmetry in between both, right? In which you have on one the 0.3 and on the other the 0.7. Right? Any questions about this, guys? I'm really sorry for the mousing. I don't know why it's happening. Maybe it's because I'm using the second screen. Could be. Okay, any questions, guys? Okay, if there are no questions, then let's go quickly. I know that we have just 10 more minutes, but let's go quickly towards R in order to do some modeling. All right. And I prepared a really good document for you guys to check on how ARs work, how MAs work, but we'll just jump to the part of modeling. Share screen. There we go. Okay. So I'm gonna post this document for you guys. I've explained what's time series and ARMA models, what's stationarity, what are AR models, what are MA models, and then this is what we'll do right now. So exploring data becomes most important in time series model, and without this exploration, you will not know whether the series is stationary or not. I mean, you can just look at it and guess if it's stationary, but you won't know for sure if it's actually stationary. So in order to do this, let's use a data set that's already in R, that's called air passengers, and it's a time series from the year 49 to 60 of monthly international airline passengers. Now we're going to use the preloaded time series object in R, which is called a TS. Now there are other type of time series objects that build upon TS. The most probably known one is XTS, which is called extendable time series. But for now, we'll see this one. So we load the data, and we check if it's a time series object. It is, and I think so. This is clearly formatted, but I think it's better if you guys look at it on my Art Studio. So what this is an art markdown document. So it's like a fancy way of looking at our documents. Okay. All right, let's load the data. Now, is this an time series? Yes. Let's look at it. So how TS object work is that you have it prints out depending on the type of the data. Now it knows that this data is monthly, and also it knows the years. So it prints it upon January to December, all throughout the years on the data set. Now, let's look at the data and let's check some functions. Let's check the summary of our object. The summary of our object tells us, since it's a numeric object underneath the TS, then we have the minimum value, the first quarter, the median, etc. All that the usual summary function gives us of a numerical data set. Start tells us when our data set starts. Since the year is the one that's primary on the function, then we have the year 1949 and the month January. So one. Just like start, there's a function called end. It tells us that our data set ends on December 1960. Time, how many? What is the time of each one? So in this case, our data will be formatted as the portion of the year. So you know that months are all throughout 1 through 12. Now this makes it into a proportion of the year. Okay. Also frequency. Frequency allows us to know how many months in the year, or if you're looking at a daily intraday data, for example, and you're looking at hours, then it'll show, for example, 24 because your data is in hourly presentation. If it's in seconds, then you'll get 60, so 60 seconds in 1 minute, and so on. Let's look at it. So the most important thing when you have any kind of data is visualizing it, because you can get a lot of statistics, but with visualization, you can jump upon some conclusions faster and know how to tackle your data and from what angle to look at it. So this is our data. You can clearly see that there is one, a trend, an upwards trend. Two, is this series mean stationary? No, it's not mean stationary. It's variance stationary. Nope, it's not very stationary because look at the bumps. Over here, the bumps are really small. Over here, they are really large. So it's heteroscedastic. Clearly, there's a trend, right? This is a simpler regression with our time and the number of passengers. So now let's look at autocorrelation. So our autocorrelation function is given with the ACF command. And what it does is it calculates our autocorrelation with lag 1, lag 2, lag 3, all the way towards, in this case, these are months and part of the years. These are years, by the way. So these are autocorrelations. There's clearly none of them that falls within the standard error, the confidence interval. Okay. So that means that this function is very autocorrelated. We cannot use functions that are very autocorrelated, right? So we have to correct these things. If we want to fall into pitfalls, we can, but we have to correct this. So in order to fit the data, we can use, for example, an AR1 model. Why? Because our AR1 model, let's go back. What it will do is build upon the last value increasingly, right? So it'll capture this upward trend. Okay. So in this case, what what R does is it doesn't just use AR or MA. What it uses is this function called ARIMA. So I say the expansion of ARMA. The first term is the AR term. The second one is the I. So how integrated is the function? We'll see about the I later on the course. But for now, think of it how many times you have to differentiate the series. Okay. And MA is the moving average term. So this is an ARIMA 100 is a AR1 model. Okay. So by fitting an AR model, we get is this. We get an intercept of 278, so around over here, and an AR that's really, really close to 1, but it's still lower than 1. Okay. So there's a lot of persistency in our model. Okay. If we plot our data again and we show the difference in between our data and the residuals of the model we just generated, we should get the model, right? So this is how far our model captured the series. It's pretty close, right? So an AR model, an AR1 model, looks pretty good, right? Let's try an MA model. So the same way as ARIMA 100 is an AR1, and ARIMA 001 is an MA0, an MA1. Okay. These are our output. Now, what can you look into these outputs? If you were comparing different kind of models, a useful indicator to look at it is the information criteria, Akaike information criterion. Okay, you want this to be the lowest possible. So this one is 1,428. This one is 1,618. So just by eyesight, this one should be a better model. Let's test it out. So we saw how close our AR model plotted our data. Let's see how our MA model plots our data. Not quite good, right? And yeah, I'm gonna leave this one for later. So forecasting, we're going to push it forward. But guys, any questions before ending the class? No? Okay. All right, guys. So I hope you guys have a really good week. Study for the test. I will upload some. So you will have more exercises than just the ones that you just saw in order to practice. You can consult maybe your econometrics 2 friends for material. They also see this topic in econometrics 2. Not we will look more in depth later into this topic, but just up until this, you guys should be on par with them. And yeah, have a good one, guys. If you have any questions, you can make them to Jesus or I. Hasta luego esta semana. All the things that you see up until the next Friday. Mhm. All right. Very well, guys. We'll see you next week. Goodbye.